Hey guys, I'm going to be going over the models we treated in class. So this is the first model, the plate capacitor. Okay. Before I proceed, I tried logging into the PC pool at room 3109 TMZ, but I couldn't. I wanted to log in so that I could use CST 2018 so that any problems I encounter you could also see it and then know how I navigate away from it. But unfortunately, I could not. So I'm going to be using my version of CST, which is CST 2022, and hopefully you don't encounter much of an error. I think the errors we had in class was due to us exceeding the amount of elements we the license allowed. So if you notice any problem, just check the um log file for the simulation. I would also show you. If you notice any problem, just check it and see if it's written there that the mesh sizes exceeds the permissible amount. So let's get right into the modeling. I won't go over the theory. You could look at this yourself. I'll just focus on the modeling. So this is what we want to model and simulate. So I'll try and go as slowly as possible. Now let's model the capacitor. Now the first thing you need, of course, is your setup. So open CST Studio. So it's already open over here at the left to make it easier. And then in the modules and to select 3D simulations, then select low frequency. So 3D simulation, and I select it, left clicking, and then I select low frequency. So it brings up the interface. Now let me make this a little bit smaller. Yes, so I have more space here. Now we are done with this slide 7. Now this is just a description of the toolbar, main menu, navigation tree, and units. Now in the home tab, setup solver, select static solver. So these are your tabs. So you have the home tab, the modeling tab, the simulation tab, the post processing tab, and the view tab. So these are your tabs, and this should be your ribbons. But I mean, using Microsoft, this should be your ribbons. But let's see. So the home tab, you have to select. So in the home tab, so if it wasn't in home, you click on home. That you click on home, and then you go to setup solver. So this is setup solver, and then you select it. Now be careful, because if you select this, now you see that as I'm moving it up and down, you see that the blue highlight shifts. Now if you should select this, it brings up the solver settings. You shouldn't select that, you should select the arrow instead. So solver setup, and then this brings a drop down of the possible simulations that you could carry out, low frequency simulations. So now we want a static solver, so I click on it. Now we are done with this slide. Over to the next slide. At the bottom right, select an appropriate project unit settings. Now the settings that were selected for this is meter, hertz, Kelvin, and seconds. So at the bottom right, you see here, you can see my mouse. At the bottom right, you see here meter, hertz, seconds, and Kelvin. So you could click it, and if this wasn't in meters, you change it to meters and hertz, and just to correspond to what you have here. And then since there was no changes, I just have to cancel out. Now we are done with that. Now in the simulation tab, click on background and limit the background and the surrounding space. So simulation tab, which is this, now click on background, that's this, and then it brings up this pop-up. Now we have to limit the background space. So your background space is like your environment. So the environment where you want to model the capacitor in, and in this case it's going to be normal, which is air. And let's see, we want to create a 1 meter box and then apply in all directions. So if you look at this, this matches this exactly. So that's that. And now, just a side note, I could also show you the background in view. Okay, because I have the CST studio kind of squished in the horizontal direction. Some of these buttons are hidden, so I could go not dimensions, visibility. I could view the bounding box. So the bound, if I should view the bounding box, that's the environment. So this is the box we just defined by applying 1 meter in all directions. So I just press 6 to view the right, and then I could also press 3. So you have that. This is the bounding box, and this is going to be filled with air because it's the surrounding we want to observe our capacitor. So that's that. And then we go over to the next slide. Now in the modeling tab, click on brick. So I could, okay, I'll leave this here. I don't want to turn it off. So you go to the modeling tab, and then you click on brick. So these are kind of primitive shapes that you could use. So this is brick, as you can see. Then you see sphere, cone, torus, cylinder, and you also have faces and apertures. But then we want to create a brick, so click on brick. And then once you click on brick, it brings up this red dot, as you can see. Now you could draw the brick with this dot, but then it won't be very accurate, so you just click on escape. So your escape key, I don't know what this would be on the German keyboard. I think it should be escape. So the key to the top left of your keyboard, escape. So when you click on escape, you have this pop up, and then you'd copy the dimensions from this. So minus 0.5, be careful when copying the dimensions. 0.5 minus 0.5 and 0.5, and then 0.05, and then 0.1. So once you are done, you also change the material to PEC. That's perfect electric conductor. So I could also preview. So when you click on preview, you see something appearing. So I could view the front side or the side of it. So you see it here, and if you're satisfied with it, I mean, you cross check your dimensions, and then okay. So you have one of the solids. Now let's go over to the next slide. We need two. So this slide and this slide, they look the same, but then they are not. So slide 12 and slide 13. Now we need another brick. So just repeating exactly the same thing. Click on brick and then escape. So you could also see a double click the first point or press escape to show the dialog box. So I click on escape, then I copy this dimension. So this is minus 0.5, 0.5, minus 0.5, 0.5, 0.5, and minus 0.05, and minus 0.1. Just be careful when copying dimension, and the material is also PEC, so your perfect electric conductor. Now as you can see, we have two parallel plates. So we have our model geometry. Now on to slide 14. In simulation tab, click on boundaries and apply the appropriate boundary conditions. So in simulation tab, you click on the boundaries and then you apply the appropriate boundary condition. So the appropriate boundary condition for the bounding box is open boundary, since the space is continuous. So open boundary could also use open boundary add space, but then we don't really need space because we've already added the space by defining 1 meter background length, width, and breadth. So open, and then you apply open to all of them. You could just click apply in all directions. So then okay, so we've applied the open boundary condition to all of these faces of the background. Now over to the next slide. In the simulation tab, click on electric potential. So this is a capacitor and we want to apply some an electric potential, so we have a potential difference. So we click on electric potential. You could click on this, which would give a drop down of either field grading or electric potential, but now we need electric potential. So simulation tab, electric potential, and then when you click on it, it asks you to select if the face of a particular solid. So we want the left, so we could select any of the faces. I think this, and select face, and then press escape to complete the press return. Sorry, not escape, press return to complete. It's written here, press return to complete selection. So I select this, double click, and press return or escape to leave this mode. So when you see this, it means nothing is selected, but then if I double click, it selects. If I double click again, it unselects. So be careful to see that this doesn't show press return or escape to leave this mode. I double click, then press return to complete selection. So once I press return, I see this pop up to define the potential. So the potential value is -10. Okay, there's a slight difference between this version of CST and this. In this version of CST, the one used to create the tutorial, there's no folder, but then ignore it. So all we just need to do is to input the potential value, which is -10 volts, and then fixed. Yes, 0 degrees phase. Okay, and so we have that on the left, side of the capacitor, the left capacitor plate. Now for the other one, we go to 16 and wait, I think I missed one slide. No, in the simulation tab, click. Okay, in the simulation tab, click on electric potential and apply -10 volt to one plate and 10 volt to the other plate. So we repeat exactly the same thing for the other plate. We've applied -10 volts. Now it's time to apply 10 volts. So click on electric potential and then click on this, double click, and then return to complete selection. Then 10 volts. So plus and minus. So okay. And then we have that we've set two potentials. So as you can see, blue and red, -10 and 10, and you can also see here the potential. This gives a total potential difference of 10 minus -10, which is 20 volts. This is important later, I think, if I remember correctly. So we are done with slide 15. So be careful to apply -10 and 10 volts. Then slide 16, over to the meshing. The meshing is automatic, so you could go to the home tab and then click on mesh view to see the mesh, or you could also view the mesh from the simulation tab. So let's go to the home tab and view the mesh. Now, since the mesh has not been generated, when you click on view mesh, you don't see anything. Now to generate the mesh, you just click on update, and this updates the mesh. Now you can see the mesh for just one of the solids, and that's because just one of the plates is selected. To select both of them, you either click on components, that's to select all the components, or you could click on the plus sign to drop down, and then you could select either, and holding your control key down, you could select two, but then it's easier to select everything, so you just have it there. So you see the mesh. I clicked on 3. Remember your navigations: 3, 6, 4, 5, 8, and 0, I think, and 2. So you have your mesh, and then go to in the global properties. The initial setup of the mesh could be varied. So if you should go to global properties, you could have different settings here. So currently it's 10 cells per maximum model edge. So this just controls the fineness of your mesh. So I could change this to 20. It makes the mesh finer. Okay, let me do that. So that's, and I'll change it back to 10. So once I make it 20, I can update and you would see a finer mesh. Okay, and then mesh view again. So you see we have a final mesh, but I'll take it back to 10. And okay, and mesh view, and I can update. So we are done with slide 16. Now over to slide 17. Over to slide 17. Now in the home tab, click on setup solver and start the simulation. So if you just click on close mesh view and then it closes the mesh view. Now on the home tab solver, you can now click on setup solver. Now instead of clicking the drop down which allows you to change the type of solver, you now click on this button, so the highlighted ES. Either that or you can go to simulation and just click on setup solver. Yes, just one button, not double button. So you just click on setup solver, then we try to match it here. You could also require a more accurate solution, and so currently we do not want to do any adaptive mesh. So we do not want the mesh to be made fine and then convergence should be studied. We don't want that for now. So we just run it once for the parameters we've given. So on the home tab, click setup solver and start simulation. So start simulation. Then it's not a very big model, so it doesn't run for very long. So the results are out. And then now what do we want to see? The electric field and potential could be observed in the 2D and 3D results. Then how does the electric field look like inside of a PEC? This is the result. Now how do we view the result? If you see here, you could expand your 2D and 3D results, and then you have your E field, and then you have your D field, and then you have your electric energy density ES, and then you also have your potential. So we could look at the E field, and what you see is a 3D view of the E field with the bounding box. I could at this point turn the bounding box. Okay, I'll leave it. I'll leave the bounding box. So you could turn off the bounding box, still go into view and then show. No, not show. Bounding box. Okay, it's now expanded. So you just turn it off. But I'll leave it on. So now we have this result, but then it doesn't look like what we have here, and that's the reason is because we are viewing the entire 3D result, so we see lots of overlapping arrows. Now to view just a slice, which is a plane of it, we go to 2D and 3D results. Now you see that there's a specialized tab for the results, so 2D and 3D results, and then you could get a sectional view, which is what we need. Now this is collapse. I think maybe I would increase it a bit so you see how it would look. Yes, so you would see this normally fields on plane, but then since it's collapse, what you have is sectional view. Then when you click on it, you see the different settings for the sectional view. So fields on plane, so you could click on cross section A, cross section B, cross section C, and cross section D. Let's look at what cross section A holds. So cross section A, and I press 6. So this looks like what we have here, but then I'll just have to tilt it a bit. So control, hold down control, and then your left click, hold down, and then drag. So this is what we have, but then to view the solids also, I could go to comment. So this is solid, selected, yes. Currently I still can't see the solid very much, so I think that the view is wireframe. Okay, it's actually correct, but then why can't I see the, or they not selected? Okay, they are selected actually. Maybe I could turn it over this way, or maybe turn off my bounding box. But then yeah, that's it. You have the field. I don't know why the geometry is transparent. Okay, this is wireframe. Show Orthographic sectional view, cutting plane. Wait, let me expand it. I know why it's. I mean, you could see the solid, but then it's. I want it to match the figure to the left if I can. So arrows. Mm, mm. I think maybe it's in my settings. Working plane, shape accuracy. I think if I should, I don't know. Okay, I think it's dependent on the settings you have in this, but then it's not important. So I'm just going to cancel it out because now making it opaque, you could see the model clearly now, but I think I'll just leave it as it was. Cancel out. Yes, I'll just leave it. So this is what you have on this particular plane, which is what you have on this figure here. Okay, collapse it now a bit. Yes, so this corresponds to what you have on this figure. You could also move the slice. So the slice is just at the edge. You could also move the slice inside by so your 2D 3D plot, and then your sectional view. You could change the location. So I'm going to change this to 0. So this is what we have, and then you could just view the section of it. Okay, just one is selected. Yes. So this is what we have for the electric field. Now, this corresponds to the potential. This plot, and it's not an arrows plot, it's a contour plot. So you could also change the electric field to contour plot, and then you see the electric field as contour, but then it's better viewed as arrow. So you see the field. Now for the potential, this is what we have, and you see that it corresponds to the image that we have on this part. Now you could also look at the electric field energy, which is a scalar 2.53 joules, and then you could look at the charge value, charge potential, the potential, the charge of the potential, yeah, and then open boundary conditions. You have this. Now, 1D results, you could also find some interesting results there, but we are not really interested. So the E field maximum, the energy background, but then we're not interested in any of this currently. So over to 19. Now, in the global properties of the mesh, change the cells per model according to the following setup and fill the blank spaces. So I think this is pretty straightforward. You can do this on your own. So in the global properties, remember the global properties that we looked at. So you have your global properties. You could also look at, so in your simulation tab, you could also see this in your home tab, global properties. So like I said, this controls the fineness of the mesh. Now you could also click on this, which is the drop down, and then you could select whether it's tetrahedral or hexahedral mesh that you need for your model. But then yes, so all you need to do is change this is already 10. So once you solve with 10 cells per model box edge, you get your results. Now you'd have to record here the number of tetrahedrons. Now you see that it's written here clearly for you, 3471 tetrahedrons. So you write it here. Then the energy field, the electric field energy in nanojoules, and you get this from this. So you have the electric field energy. When you double click, you have the electric field energy, total electric field energy, and that is 2.53 e raised to power minus 8. So in nanojoules, that would be 25 nanojoules. So you record it, then you go over to your global properties and change this to 12, and then the background 2. So this to 12, and then the background 2, and then you run the simulation again. So I'll do it for this. So I've changed it to 12 2. I can apply update or just click OK to leave. Then it tells me it wants to delete my current result. I'll say yes. And then I go over to simulation. Setup solver, the same settings. I start and it solves, and it's pretty fast. I don't know if I think it should be my system. So then the electric field energy 2.50, so 25.04, and you continue repeating this until 22 and 7, but then I think the CST version we're only able to get to 14 and 3, which is also okay. The point of this is to show that with much refinement, the more you refine your mesh, the more accurate, or your value converges, your result converges to a particular value. So that's the goal of this, because when you plot the energy versus the number of tetrahedrons, you see a kind of convergence. So it's converging to one value, either downwards or upwards. Now, in the home tab, click on setup solver and then adaptive meshing. So this is kind of us manually checking for convergence. So we go through the stress of varying these values and recording a number of tetrahedrons and then plotting it, but then we could also do that automatically with a particular condition. So if you should go to the home tab, which is home, now click on setup solver, which is setup solver, either your home tab or your simulation tab. You click on setup solver, the top button, and then click on adaptive mesh refinement and click on the properties. So the properties, insert the shown values and then run the simulation. So the minimum number of refinements, this just define the minimum number of refinements we want, and then the maximum. So how many stages of refinement we want. Then the stopping criterion, the smaller the number, the more fine our mesh would get. Then snap new nodes, that's not important. So we just have to make this match. If you want more accuracy, then you would have to increase the values to maybe multiple numbers of zeros. So refinement 10%, 2, and maximum 8. So after that, we click on OK, and inside the known values, then run the simulation. So run the simulation, you start. So this is going to take, okay, maybe not very long because it's already in pass 5. So each pass is a level of refinement. So we have pass 1, which is your default, which is your starting, your initial mesh resolution. Then you have pass 2, it refines it. Pass 3, pass 4, pass 5. Then if it satisfies the condition you gave, which was the stopping criterion before 8 passes, then it stops automatically. Otherwise, it gets to 8 passes, and whatsoever the accuracy is there, it stops. So you don't run the simulation forever. Maybe it doesn't converge. I mean, some solutions would not converge to the particular accuracy that you require. Now, in the navigation tree, go to 1D results and then adaptive meshing. And then the energy, the number of mesh cells, the solver time could be observed. So the number of mesh cells, remember on this slide, we would have written this by ourselves and then put width for these values. So you see that for each pass, so this is pass 1, pass 2, pass 3, pass 4, pass 5, pass 6, pass 7. The default should be the kind of 0, so you have 8. Or maybe it finished in desired accuracy reached in I think it's pass 7 coming. Yes, in pass 7, the desired accuracy was already reached in pass 7, so it stopped. So there was no pass 8. So you see the number of the mesh cells, then you could also look at the energy. So the energy is converging to a particular value. Now it looks like it's still kind of varying, but then you have to observe that these values are really small variations, and to kind of view that really well, you go to 1D plot. Now whenever you click on a 1D plot, you have this specialized tab pop up, and then on the 1D plot you could view the y as log, and then you see better the convergence. So you could see that this is almost a straight line in log form, but then in your linear form you have this depending on the scale that you use. So this is 2.505 and this 2.465. Now the difference between pass 6 and pass 7 is not very much, the difference in value. So you could also see the time. Of course, as you increase the number of mesh, the time it takes to run the simulation also increases, and then solver time. You also have that it increases. This is 3 seconds for this mesh resolution. Now, I think in class we also had the problem that we could not get to the, because we have 105,000 tetrahedrons. I think the maximum in class was 40,000 or so. So if yours doesn't get up to um 7 passes, then maybe you could, what could you do? Maybe reduce the number of passes. So maybe just to 4 or something, and then you'd have similar plots. Now, so we are done with this slide. And now, what is the relationship between the number of mesh cells, error, and solver time? Of course, you see that number of mesh cells as it increases, as the number of mesh cells increases, then what you could also do, you could also select 2 plots, but then depending on the scale, you might not really see so much, depending on how different they are. So you see here, as the number of mesh cells is increasing, the error is reducing, right? Perfectly, the error should be 0, but of course it tends to 0. So you have that as the number of mesh cells increases, the error reduces, and then as the number of mesh cells increases, the pass time also increases. Now, find the capacitance of the parallel plate capacitor from the total electric energy. Calculate the capacitance from the analytic formula. So you should calculate this from the analytic formula using the area. Where can I say that? So the surface area of the capacitor, and and then yeah, permittivity, and then the separation. Now remember, the separation is, I think we used, where is it? Oh boy. Yes. So the separation is 10 centimeters. So once you input all these parameters, you get a solution. Now the task here is to compare the relationship between your analytical formula and your analytical result and the result you got from the simulation. Now to calculate your capacitance from the total energy, come in, I don't know where I'd write this formula. Okay, so I snipped the formula here, and then let's calculate for one instance. Now find the capacitance of the parallel plate capacitor from the total field energy. So this is the, you use the total field energy, and then your C is your capacitance, and then V is your potential difference. Now we know your potential difference and U. So I'll just type in the values here. Hopefully this works. So U that we have is 2.65. I think maybe I could copy this. If I can copy, maybe I could paste it here. Yes, I can. So 2.65 times 2, and that is equal to this, then divided by, I need brackets, scientific. Okay, now I have to start all over again. So I can copy this, and then my calculator, if I can find it, paste, and then this multiplied by 2, then divided by v square. So I need brackets. Oh, come on, where are the brackets? Okay, I'll just divide it by 20 twice. So 20, then this divided by 20. So that's 20 square. So what we have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's see, 11, 12. So let's say 123. Oh, this is correct. This is 123. That's minus 12. So that should be picocoulombs. Yes, I mean, hopefully that's correct. 123. Maybe let me just confirm with my calculator. So 1, 2, yes, 123 picocoulombs. Yes. So where can I write that? Okay, I think I can write that here. So this is 123 picocoulombs, and then for the analytic formula, what we have is let me see, clear. Okay, I've never really used this before. I think it's C. Yes. So what we have is permittivity. I think that should be approximately 8.854 e to minus 12. Come on. Oh dear. 8.85. Okay, it's e to minus 12. So I'll just leave it as pico. So that's the pico part. And then times the area. What's the area? The surface area, the cross sectional area is 1 times 1, which is 1 meter square, and then divided by what? What is it? Divided by the separation, which is 10. Now be careful. This is the separation between the faces of the plates and not 20, so it's 10 centimeters. So that should be divided by 10 raised to power minus 2, which is divided by 100. Is it? 10 raised to power minus 2. Is it? Wait, divided by converting 10 cm to meters, that's 0. 0.1. So divided by 0.1, yes. So this is 88.5 picocoulombs. So this is 88.5. Okay, 8.854. So 88.854 picocoulombs. So these are the two capacitances we calculated. I moved this away for a while. Now, which of the following is correct? C3 is less than C no 3. Now, this wasn't mentioned initially, but what we actually simulated was for the case where you have stray fields. And what do I mean by stray fields? Let's look at the electric field profile again. Now, you have that any field that is not part of your capacitor. So, if I should put the bounding box around the capacitor, okay, this is twisting, but then if I should put the bounding box around the capacitor, you have that all other fields are stray fields. So what we simulated is for a capacitor with stray fields, which is the real capacitor. But then this formula was derived assuming no stray fields, and that is why we have different results. Now, which of the following is correct? Is the C, the capacitance, and this might be important for your exam. Is the capacitance with stray fields, is it less than that with no stray fields? Is it equal to? Of course, it's not equal to. Now, the capacitance with stray fields is greater than with no stray fields. So this we just calculated is 123, which is greater than 88.54 picocoulombs. So the correct answer is this. Now, take note of this. Now, let's see how we could simulate the case without stray fields. Now, in the background properties, change the distance of the surrounding space to 0. So we go to, where do we see background modeling or or simulation, one of them. Simulation, you go to background, then you remember we applied a space around it, which is modeling it in the environment, right, which is with which is interacting around the air. But now we want to limit that space and make it 0. So we do not want any surrounding. So it would ask to delete the result. Yes. So you see that your bounding box is now limited to just the capacitor and the space between them. Now, what next should we do? In the boundaries, we need to change the boundary conditions to magnetic HT is equal to 0. And this in CST means that your normal electric field, which is we are limiting the electric field to just this domain. So we do not want any electric field sticking out, which is your normal electric field equal to 0, which in CST is tangential magnetic field equal to 0. So we go to simulation boundaries, and then this was open initially. We change it to HT, which is magnetic. HT is equal to 0, and that's it. Then we repeat the simulation. Should I repeat it with? I'll turn off adaptive mesh refinement so that we have solutions quick. So it's done, and then we go back and check the energy, the electric field energy, and now it's 1.71 e to power 8. So I perform the same calculation with this, and I think I'll click on this. Yes. So 1 point this multiplied by 2. Yes, then divided by what, v squared, so divided by 400, and that is 88.5941. So approximately this. So for this, the capacitance is 88.59 picocoulombs. So you see that limiting the fields just to this region and imposing the boundary condition that the normal electric field should be zero. Then we have the no stray fields condition, and it tallies with the analytical solution. Now we could also view the electric field, and then you see that there are no stray fields. So all the field um, are confined within the space. So this is what you have. And yes, I think that was it for the tutorial. Now you just need to cross check your results and question them, which is of course what we did here, to see, okay, why the discrepancy between the analytical value. And also one thing to have in mind is that most of these analytical solutions you have, or maybe a handful of most of them, are usually derived after some simplification is made, some assumption is made to simplify the problem, so that you could easily maybe differentiate or easily integrate it. So what we usually have is not I realistic most of the time. It's just an approximation. So there's that. Then I think, why do we need boundary conditions? Of course, to properly define a problem. I mean, without boundary conditions, you really can't solve your problem. And okay, you can solve some problems, but then it won't. Okay, yeah, because for your eigen, okay, even for your eigen value problem, you have that your boundary condition is zero, so homogeneous solution. That's what you're having. So you have your boundary problem to define the physics. I mean, to complete your model. Without it, you won't be able to solve your problem. And then you see that different boundary conditions result in different solutions. So the impositions you have, the constraints you have at the surfaces, which are physical constraints, of course, not just something you made up, but then physical constraints of nature. You put them, and then you have different solutions. So why do we need a mesh? Now remember, this is, we use tetrahedral mesh, so we are solving your finite element. But your discretization was um tetrahedral. So is it, yeah, tetrahedral? And then I don't know if you've um taken a class on numerical mathematics. So we are actually solving this problem numerically, and for this we need to discretize our domain, and that's why we need a mesh. And for this case, we are using a finite element method to solve it, and that's why we have to discretize it, so that we get, of course, this would result in a linear system of equation. Now, how do we choose the mesh? Is it better to be dense or coarse? Now you've seen that we did a convergence study. The finer the mesh, the better the solution. Now, what is a convergence study and why do we perform it? Now, it still boils down to cross-checking the results. Still boils down to cross-checking the results. You could put anything in the system and then you have a result, but then if it doesn't match with reality, then maybe your model is wrong or something else is wrong. And then you could also have a solution that may be close to the result for some cases, but then far away. So we always have to do convergence studies to see, okay, what is the error that we have? Because of course all numerical solutions, they are never exact, but then there's a particular tolerance that we are okay with. So that's what we did the convergence study with. Okay, we are okay with an error of maybe 1 e to power minus 8, right? And then we won't know what the error is if we just solve one problem just with one parameter. We don't refine the mesh and see how the solution changes with it. So that's why we do the convergence study. So I think that's it for this problem, and hope you learned a thing or two about it, and hope you can follow the tutorial yourself. um I'll do for the other ones.